Good morning and good afternoon to everybody, depending on your time zone. I have the pleasure of introducing Dr. Brett Sanders today. He is the Chancellor's Professor of Civil Environmental Engineering at the University of California, Irvine. He currently serves as Director of the UC Irvine Climate Collaboration, an initiative that brings together expertise from many different disciplines and community partners to address urgent climate resilience and sustainability challenges in Orange County, California, and beyond. His research seeks to understand compound and interconnected climate risks, especially relating to flooding, and he presently leads collaborative flood modeling projects in California and Florida. He is a fellow in the Engineering Mechanics Institute of the American Society of Civil Engineers, a fellow of the Environmental and Water Resources Institute of the American Society of Civil Engineers, a fellow of the International Association for Hydro Environment Research, and many other honors and recognitions. Please join me in welcoming Brett. Brett, we're really looking forward to your talk.
Well, thank you, Alex, and thank you everyone for the opportunity to join you today. This is really a lot of fun. So I'd like to talk about errors in flood inundation prediction. And the idea today is to kind of give you some background into shallow water wave modeling, which is my academic background. So when I went to grad school and, was working on, topics, this is something that I got into really early and I've been doing my whole career. And working on methods like PRIMO, which we use now to try to do flood inundation prediction at larger spatial areas and making it faster and more efficient. And then I'll get into some comparisons of PRIMO with First Street data, at least across Los Angeles County, where we've done some work, and then kind of summarize some takeaway points. So a little bit of acknowledgements here. We deeply appreciate funding we've had from the National Science Foundation, from NOAA. National Centers for Coastal Ocean Science has been a supporter of our work. We've had support from NASA, especially along sort of remote sensing of topographic change and implications for risks along the coast. And the work is like a big team effort here. Joe Schubert, Daniel Collin, Eva Martin from UC Irvine, on their work will kind of be featured today. And Catherine Mock at the University of Miami has been a significant collaborator for the last 5 years or so, along with Mike Sukop. So that kind of anchors our Miami team, and we have our Los Angeles team. And we're really indebted to a whole lot of government and non-governmental organizations that help us with our work. We try to, work with organizations that care about flooding and have information about flooding, and so we appreciate those collaborations for making our work better. All right, so let's get into the shallow water wave modeling, and floods are described by really well by shallow water wave theory, and the main assumptions in shallow water motion is that the pressure distribution is hydrostatic. So as you go downwards from the free surface, you're just saying pressure is increasing linearly with the unit weight of the fluid. We do a depth averaging of the water column, and so we end up resolving like a depth average velocity. And then we use a drag law for flow resistance, and that can be parameterized with different types of parameters, like a Darcy F or a Manning N or a Chedley C. There's different ways you can do that, but that's the gist of how most floods are described, and they're described really well with that model. What I'm showing here is just a one-dimensional model, but I'm showing it just to kind of, we do flooding in 2 dimensions, of course, but just to kind of illuminate some of the key features that we try to resolve, like the depth of flooding H, the depth average velocity, or the product of depth and velocity, which we call the discharge per unit width. And we'll predict that as a function of space and time. And the key inputs to do accurate flood modeling are topographic data, resistance parameters, and then we get into infrastructure and, of course, the sources of water. How much water is coming into your system? Is it coming from rain? Is it coming from a storm surge? Is it coming from stream flow? The sort of shallow water equations can be reconfigured in a characteristic form where you basically go from 2 partial differential equations to a set of algebraic equations that the velocity plus twice the wave speed is a constant along these characteristic paths. And lends itself to some nice analytical solutions. And of course, so the wave speed just goes as the square root of GH, and the Froude number is a key dimensionless number, that's the ratio of the velocity to the wave speed. So I want to point out here, because we'll kind of circle back and explain some of the differences that we see between some of our predictions and some of the first street predictions. But when you have subcritical flow, so a Froude number less than 1, you end up having, this is space and this is time, you have information moving in both directions. So you have basically, disturbances of the flow can propagate downstream, and disturbances of the flow can propagate against the current and move upstream. And because of that, you can, of course, with the method of characteristics, you can always take solutions at 2 points and predict them at some other point. But this also informs boundary conditions. So if you want to simulate flow, you need to know something of what's happening upstream, and you need to know something about what's happening downstream to accurately characterize the flow. When we get into supercritical flow, when the velocity is greater than the wave speed, both of the characteristics are moving down in the downstream direction. And so you basically need two bits of upstream information to predict what's going on downstream. And you don't need to know anything downstream to predict what's happening upstream. So everything just moves in the downstream direction. And then basically the direction of these characteristics have informed numerical methods. Like under subcritical flow, you could argue that like a more centered difference approximation makes sense. And under supercritical flow, you could argue that an upwind method is better suited to solving the partial differential equations. And but with these analytical solutions, and a dam break problem is like a classic analytical solution that we'll use for testing of methods. You get like a wave moving across dry ground, and in the case of it with the downstream bed initially flooded, you get a shock wave forming, or hydraulic jump as we call it. But both of these things, both the hydraulic jump and this interface between dry land and wetland, are discontinuities. And these things have been the thorn in the side of a lot of numerical methods over the years. Many methods have struggled with wetting and drying because the depth goes to 0. If you try to divide by depth, you end up getting a singularity, and you get really lousy model performance along the way. So for years, like through the 70s and 90s, researchers would sort of try to develop finite element methods, finite different methods, all sorts of methods to try to come up with robust solutions of shallow water equations to better predict flooding, to better predict irrigation dynamics, to better predict canal flows, dam break flows, all sorts of different types of flows. And so the key issue that people confronted, and I'm sure you see this in atmospheric sciences too, is that if you go, if you have like a Galerkin method, which is kind of a centered difference type philosophy, you end up, if there's a sharp front, you end up introducing oscillations because you have these dispersive errors. And if you go with something that's like an upwind method, or you add a lot of numerical viscosity, you smear out the solution, and your sharp fronts become really diffuse fronts. But Godunov's method came along, I guess it was first introduced in 1959 and first popularized in aerospace engineering for compressible gas dynamics. And the basic idea is that you kind of assume a discontinuous discrete solution where you have bins or tanks, and each tank is filled with a different amount. And you have these interfaces in this, or discontinuities in the solution at every edge between neighboring cells. And that works out nice because once you have that discontinuity, it looks just like a dam break problem. And we know analytically the solution to that problem. So you can embed like an analytical solution in there, get the fluxes based on the analytical solution, and then advance the solution in time with like an integral conservation law. So you update the solution at the cell center based on fluxes at the edges. And that's worked out really beautifully for shallow water flows. And I happened to be at the University of Michigan as a graduate student, in the late 90s when, Phil Rowe and Bron Van Leer and sort of the people who were working on these Godunov methods were there. And it was fortunate to kind of learn those methods. And I've been using them to predict shallow water flow for a long time and try to develop methods that were more robust, able to handle a wider range of flows, that could, predict, solutions with reasonable parameterizations and so forth. On the left-hand side is an example of like a dry bed dam break test case where you have an analytical solution and some numerical predictions with different Courant numbers. And the right-hand side is, imagine a channel with a dam in the middle of it, and then you release the dam. And these are 2 gauges upstream of the dam where the circles are the measurements and the line is the prediction. And you can see the advancing wave front here, shown by the drop in the water surface. Down here, you have a couple of flood waves arriving downstream of the dam. So the floods arrive, and then you kind of see the profile of depth over time there. So the takeaway was that shallow water theory was a really nice, sufficient description for most flood waves. And really the challenges we faced then in practical application were all about, do we know the geometry of the site? Do we know like the topography well enough to predict where the water is going to go? Do we know about any flood walls or barriers or what have you? Also the challenges around how much water are we going to have? What's the height of the storm surge? What's the amount of rainfall that's going to come? What's the stream flow that we're likely to expect? And so a lot of the I think research now has been focused on opportunities with new data sources like LiDAR surveys that get a better topography and incorporating better data about infrastructure and better data about forcing and so forth. So I want to walk you through now some experiences we've had trying to predict flooding with this Primo model and showing you the kind of level of accuracy we've been able to get, just to give you a sense of what kind of accuracy is possible. What's the best you should really expect out of a flood inundation model? So the Primo model I set up, I guess it was 2019 we first published it. I think around 10 years ago I started working with this method, and I'd been working with a lot of unstructured grids to kind of deal with the need for better spatial resolution in some areas and trying to find like a good, efficient method to give you both accuracy and efficiency. But at some point, as we shifted to bigger and bigger areas, we quickly realized the biggest challenge is managing data. That, if you're working at, fine resolution data over large areas, and then you start introducing like an unstructured grid setup where you have yet another system for characterizing spatial information, just too much. So I decided, why don't we just go back to like a wrapper data structure, which is really simple, easy structure, and could we like find a way to work with that data more efficiently? And so we introduced this dual method where the idea is that we start with a fine resolution grid, which is in this case 1 meter resolution, and that data is used to characterize the background coloring here, which happens to be some topography in Miami. But this is a canal, so the canal has sort of lower elevation. And this is land on the sides of the canals. And you can see the relief of kind of the road network and things like that around this area. But the idea is we want to kind of use this 1 meter grid, or we'll call it a fine grid. Sometimes we use up to 3 meter resolution fine grid. We want to use that to resolve the topography, but then we want to kind of use a coarser grid to keep track of mass balances and momentum balances. And we want a coarser grid also because that will allow us to use a larger time step, which will be more efficient to simulate models over time. So we have references here to the details of that, but basically each time step we use detailed information about the topography on the perimeter of each coarse grid cell to compute the exchange of mass and momentum between neighboring cells. And then we sum that all up and advance the solution on a coarser grid, and then with the next time step we go back to the fine grid. So each step we go back and forth between the fine grid and the coarse grid. We use the Riemann solver to get these fluxes between neighboring cells, so that sets us up to do either subcritical flow or supercritical flow. In the last year, we've introduced a method to account for imperviousness and infiltration and groundwater interactions. That's the citation here is the last one. And the motivation here was to have a model that could be used in sort of regional scale applications, say 1,000 square kilometers or more, and still run reasonably fast. So like at 1,000 square kilometers, it's, on one GPU, the model will run like, maybe 30 times faster than real time, something like that. That's kind of where you're at. And then we also want to have models that simulate flooding under various response options, like how do we manage flooding? Do we put in more storm drains? Do we, culverts, levees, pumping, less imperviousness, these types of things? And that's been a spirit of my collaboration with Catherine Mock at University of Miami, is like, what are the response options, and how well do they align with desires and preferences of communities? And can we make modeling more interactive so more people can be involved in the adaptation process? So now getting to some accuracy checks here. This is a test case from Los Angeles. The Baldwin Hills Reservoir was located right here in the sort of, I guess, southwestern part of Los Angeles County. And in 1963, due to some differential subsidence underneath the reservoir, there was a crack and ultimately a piping failure, and a flood went downhill and inundated this neighborhood in LA. All these red dots correspond to storm drain inlets that we had access to, but the blue line shows the spatial distribution of the flood zone. And the first takeaway is that you can see that this was done by the Department of Water Resources. They sent a crew out to measure these flood zones. And the first takeaway is that in urban areas, flooding is really fragmented. Flooding will shoot down a roadway, flood one street, but not the next street. So it's pretty fragmented. And these little details in the topography, typically roads are lower elevation than the parcels on which housing sits. So those create like channel-like spaces for water to move. And so those are important to kind of get the details of your flood prediction right. And we were interested in like how well we could do if we had this first 3-meter fine grid, and then we sort of tried different levels of coarsening with this dual grid method. So on the right-hand side, I've got like a 6-meter coarse grid, a 15-meter coarse grid, a 30-meter coarse grid, and then a 60-meter coarse grid. And then for each one of these grids, I measure something called the critical success index, which is an accuracy metrics. On the left-hand side, basically it shows how much overlap there is between the modeled flooding and the observed flooding. And then I also have something here like called speed, which is sort of the speed of the model relative to this 6-meter case. So the best we did at the highest resolution, and we did this with unstructured grid models too, the best we could do was around 70% accuracy. And that was after we calibrated the model by adjusting a discharge coefficient for these storm drain inlets, how much water those inlets take. So we take that as a benchmark about as good as we can do. And then as we coarsen the grid, we kind of lose 1% accuracy at 15 meters, another 2% accuracy at 30 meters. But then we drop almost another 10% when we go to like a 60-meter coarse grid. Along the way, we take a model speed, and with going from this grid to this coarse grid, we increase our speed by 13. So the 30-meter, we're up to like a speed of 57 times faster than this model, and so on. And so we've ended up converging on this. For a lot of application, we use a 3-meter fine grid and a 30-meter coarse grid. That's kind of been our recipe because we feel that gives us a reasonable trade-off between spatial accuracy and speed. But also hope that kind of shapes a little bit of your expectations for how much accuracy you could get in a model. So more recently, this is a paper that came out just this past year where we showed like a model that incorporated these groundwater interactions, and that model was set up in South Florida, where you've got flood risks from extreme rainfall, you've got flood risks from storm surge, and this area is built on limestone, which is really pervious. And because of that, for years, the region has been able to invest in things like French drains and other types of seepage mechanisms to manage their rainfall-driven flooding. So they have a whole lot of infrastructure set up that helps water get off the street, get down into the ground, and then seep into limestone so that gets it off the street and it manages the flood risk. But as the water table in the ground gets higher and higher, there's less and less storage available in that subsurface to receive water. And so if the water table sits at a high level, for example, after a series of like astronomical high tides, then the rainfall might come and cause much more flooding than you'd see during a period when there hadn't been like high tides for a while. So And this is a really busy figure, but I just wanted to kind of impress upon you the complexity of flooding in a coastal urban area. So this region has canals, which are there for a combination of reasons. They're there partly for navigation, they're partly for water supply, they're there partly for flood management, and there's these gates which are signaled with these chevron symbols, and the gates are there to regulate the flows. And so sometimes the gates are open to let floodwater out, sometimes they're closed to hold back high tides, and sometimes so different rules for managing flooding. The pumps are symbols here with the blue dots. So all sorts of pumping takes place. And sometimes, when the gate is closed, you still have rain, you got to get it over to the outside. And so you have pumping. They also use pumping ahead of storms to try to lower the groundwater table before the storms arrive so that they have space in the ground to soak up water when it rains. All that being said, we wanted to try to see if we could reproduce the flooding in a really complex environment like this, where you had rainfall, you had a tide signal from a nearby gauge is shown here, and that gives us kind of the backwater water level. Upper right hand corner is the total precipitation over a 4-day period. So the maximum was a little over 350 millimeters over this period of time. We also ingest land use data into the model, which in turn informs like infiltration rates and impervious and whatnot, and resistance parameters. So with that as a backdrop, I'm just going to show you like how well we were able to simulate water levels in the canals. We didn't have good data on flood extent on streets, so I don't have anything to sort of check accuracy there, but we do have water level measurements at all of these crosses, which are gauges in the system. That's where we have measurements. And this map kind of designed to show you how well we're doing predicting water level. And I'll try to explain like the design of these plots here. So for each one of these plots, and I'll start in the upper right-hand corner, the blue line is the observed water level at the gauge. The red line is one particular prediction depending on a specific initial depth to groundwater. So we ran our model with an initial depth of groundwater as low as 10 centimeters, which meant there wasn't much space for storage. We also ran it, for a bunch of other values up to a value of 200 centimeters. That meant that there was 2 meters of ground that was dry that could soak up water ahead of the storm. And then the shading shows the range of flood depths that we predict depending on the initial depth to groundwater. So the red is just one realization, perhaps the best comparison of all those that we tested. And then the red shading is kind of the range of flooding that's linked to the initial depth to groundwater. And so typically when you do coastal flood model, it's usually not hard to get the coastal water levels right if you're working off a gauge or some nearby measurement. That's usually going to be okay. Clearly, if you're trying to rely on storm surge models and tide models and a lot of large scale models to forecast a storm, that's a different story. But for our purposes, we were taking measured water levels and then saying, could we simulate what's going on within the canals with that information? So we do okay there, and we're doing pretty well at the coastal gauges. As we go inland, eventually you get to sort of far inland where there's enormous sensitivity of the water level to initial groundwater heights. And we found it was harder to get the models right. And I think there's most likely other management activities taking place that we didn't know about that are probably driving some of these water levels, because there's another whole set of gates over here, pumping into reservoirs and things like that could be taking place that we might not have captured. The takeaway though is that our best prediction was around like an accuracy of around 15 centimeters. I think that was a mean absolute error across these coastal stations. And then we had higher errors over here in the inland stations. So another benchmark of how well you can expect a flood model to do. Okay, now I want to transition to where we have very recently set up a new Primo model, which allows us just to add rainfall and simulate runoff. And we ended up with just, this is Eva Martin, she's a graduate student at UC Irvine, and she has been able to kind of set up a model that just takes the topography and soil properties, and you add measured rainfall and try to simulate the mountain runoff into the reservoirs and through the flood system to see if we could have a truly precipitation-driven flood simulator here. So to do this, she used rainfall data from the AORC archive, which is 1 hour hourly data at 0.8 kilometer resolution. We got access to reservoir operations from Army Corps and Los Angeles Department of Public Works. We had a tide gauge water level for the offshore forcing. We had, NOAA now has a 1 meter resolution imperviousness data set that we've been using to regulate our infiltration rate, and some infiltration rate data from a soil database. But this is just a shotgun map of predictions and measurements across over 30 different gauges across the LA system, which is pretty, I think, stunning to see just as a starting point. But I want to kind of just jump into sets of gauges. So if you look at like gauges that are representative of these water levels inside reservoirs, the first thing we check is is the reservoir filling up the way you'd expect it to fill up, and we're doing pretty well predicting the filling of reservoirs. And then we also look at water levels in the gauges downstream, and we're doing okay there. We have some couple gauges where we're not doing as well, bit of a phase error there. I think I missed one thing, which is I think the average error she reported here. Yeah, the top of the screen, average error was 60 centimeters. So it's a mean absolute error of peak stage across all of the records. Okay, so how am I doing on time? I'm gonna check my watch. Okay, let me jump in here. Just the comparison with the First Street data now. It gives you a sense, like the idea there was to give you a sense of like, look, if you have all the data in the world, how well can you do? And that's been sort of what we've done so far. And one thing I wanted to mention about sort of the First Street is that the list flood model, which is developed by Paul Bates at the University of Bristol and has been successfully used all over the world, they don't use this convective acceleration term. So they neglect this term, which is fine if you have like small Froude number, then that's a good approximation and you can do a lot of flood prediction. But it means that like that you're really not, you don't have a model that's designed for supercritical flow. And it also means that if you do have steep conditions, you're still going to be, the characteristics still sort of set up in this direction. And so the list flood FP model is used by, and was basically the basis of the work done, reported by First Street and still used by Fathom. And the Sphinx model also was set up with this approximation too, because you can simplify things. So now I want to kind of run through all the different things that are different between what we did in Los Angeles and what was done that led to this First Street Foundation data for Los Angeles. So you can kind of understand when there are differences, where are these differences coming from? Or at least have a guess. We tried to kind of do that. So in terms of governing equations, I have just mentioned the flow solver is this simple inertia model in the case of the First Street. In the case of flow routing, the First Street model used a 30-meter NED data to do the flood routing. And then after the prediction of flood depth was done, in a final step, they do a post-processing step to project it down to 3 meter. But they don't actually use the 3-meter data to do the routing. So a little bit difference in how the topographic data are used. The First Street data does the correction to channel slopes. We do hydro conditioning of the DEM also for different reasons, like if we try to burn in culverts and underpasses and things like that, and we try to sharpen levees to better represent the geometry. So there's different types of topographic corrections going on to try to better set up the data to work with the model that's being used. The First Street approach, if there's a small river that's smaller than say 30 meters, then they may have a 1D channel representation for that river that's separate from what they're doing with the 1D grid, with the 2D grid. And we just rely on this dual grid method with 3-meter resolution data. Either we resolve the shape of the channel or we don't. They describe using some Hortonian equation based on soil type for infiltration. For this particular paper, we didn't have any infiltration. We just assumed it was saturated, and and lots of concrete, so it didn't account for infiltration. Storm drains, they had an effective rate of drainage based on the degree of urbanization. We used the county's storm drain data. For calibration, typically I think the first street approach is to kind of design your channel so it oftentimes it's got the capacity to match the design capacity. So they'll look for what is the design capacity of this channel and try to calibrate their model so they get that right. And we just did calibration to make sure that our street inlets were performing at the level that they're designed to perform. So like urban storm drains are typically designed to capture like say a 10-year return period or 20-year return period event. And so we just ran our model and tried to kind of adjust our sort of coefficients for the street drains to kind of get that level of capture. For fluvial data, they use a different source of information. They did a regionalized flood frequency analysis where there's a limited set of gauges, and they try to estimate what the flood peaks are going to be for those particular gauges based on other gauges. We just used data that was available across like 52 different gauges in the region. We used the same pluvial data, which is good. So we both rainfall data sets and same coastal data to force the model. So there's some similarities and some differences in how those models are set up. Now this map kind of shows the spatial differences. The first street model generally predicts much more flooding on these steeper slopes. So you see a lot of slopes, more topography, where you're more likely to see supercritical flow. You see a lot more flooding predicted by the first street method. That's the FSF is First Street Foundation. And then the Primo model is predicting a lot of overtopping of channels downstream that's not predicted under the First Street Foundation model. So that's kind of the biggest difference between the two methods for this area. And it leads to a really low level of overall agreement between the two methods. So I have some graphics here that just kind of walk us through a few neighborhoods. So you can kind of see like how flooding is predicted differently with our Primo model with no drains. Now we have our Primo model that has the drains built into it. So now we're accounting for, we're going to reduce that pluvial flooding a bit. And then the First Street data as well. So down in Long Beach, where we predicted the most flooding, First Street had a smaller flood zone. And whether you include drains, it doesn't really impact the flood zone much at all. If you go up the San Gabriel River from here, this is called Whittier Narrows Dam. It's one of the really important flood control dams in the system. And here are the Primo models were predicting sort of less inundation in this area than First Street. And this is one of the most complex like infrastructure areas in Southern California, because water comes into this basin, Whittier Narrows Basin, and the manager of that basin, I think it's the Army Corps, they can choose to either send water down this channel, which gets it into LA River, or they can send it over here, which gets into the San Gabriel River. So they have the ability to try to manage the flows across these two channels to try to manage flooding in the most optimal way. But you can see there's different maps. Our model's showing the reservoir fills up and it inundates some of the areas behind the dam. This one doesn't show the reservoir filling up. Move out to Santa Monica and over where Alex is at UCLA. This is, so here you can really see more clearly how the additional drainage in the Primo drain model sort of lessens the fluvial signal here. So all the rainfall hitting the mountains, running off through the streets. This is a 1% annual chance flooding scenario. But when we add the storm drain infrastructure, we lessen that a bit. But when you get into the First Street data, it predicts a lot of flooding on steep slopes, and I think that stems from the way they handle like the limitations of when you're dealing with supercritical flow, they switch to a different equation from list flood. I think they end up mapping it differently, and they also predict more flooding in general down here. This is now sort of a real central urban area where almost everything is pluvial. And in this case, the Primo and the First Street Foundation aren't that different, but Primo drain is definitely showing less flooding as a result of trying to account for infrastructure. And this is San Fernando is like northern LA, sort of, and it's actually a part of an alluvial fan. And alluvial fans are notoriously challenging places to predict flooding. And what's, I think, interesting here is that you can see flood zones develop that are hardly even present in other predictions. It's just really sensitive to topographic representation. Still wetter with the First Street data. And this is another, this is a sort of an area north of Inglewood, sort of southwestern LA, but it's a hilly area. And it's just meant to also show, if you get into hilly areas, the First Street data tends to come out pretty wet, bigger flood zones. So these differences tend to kind of lead to not so big differences in sort of exposed people and exposed property at the county scale. So maybe at most a factor of 2 difference. But if you get into at individual municipal scales, you can have, this is a geometric mean relative error. And so you can have a factor of 2, factor of 7 difference in between First Street and Primo data. So which really speaks to like how the infrastructure is represented. And also it impacts inequalities in flood risk that are estimated as well. So just the summary then to kind of wrap things up here. So here's my kind of, on the left-hand side is kind of my thinking about error considerations relative to flood inundation prediction. You want to ask, are we getting the volume of water right? Do we have the right amount of rainfall, stream flow, storm surge, waves? We want to ask, have we resolved important flow paths and barriers? Do we have the right topo data, infrastructure data? Have we resolved the most important flood spreading mechanisms, be it overland flow, infiltration, momentum dissipation may be important? And are your sort of ad hoc assumptions reasonable? I think that's where this can be a big contributor to differences between models. Some models mask out areas behind levees. If you assume that the levee protects people, then those areas will be masked out and not predicted to be flooded. You might assume that the channel capacity equals the design capacity, but the reality is that there's things like sedimentation, and there's vegetation that fills up channels over time. Channel capacity changes over time, so it may not actually be at the design capacity. You might assume that levees overtop without breaking. That's something we do, which may not be a good assumption. So then on the right-hand side, I have what seems to matter most for bias, special treatments for steep slopes. So I think we saw a big difference in the steep slopes between the 2 methods. Whether you represent urban drainage, how you represent it, that's going to change. Definitely the urban flooding piece. How you represent levees and dams, groundwater interactions, certainly like in the Miami area. And our experience, if you overly coarsen a model, you're going to smear out the flooding. It's going to predict a bigger flood zone, usually with a coarser grid than you would with a fine grid. So kind of takeaways here is we would really benefit from more CalVal data. Gauges and streams are helpful, but don't tell the whole story. And we're looking forward to some of these newer sensor technologies coming along, like FloodNet, which is getting measurements inside the cities, and different types of remote sensing methods. And just a summary of our sort of errors in large scale applications. Like we did a Harvey model. Our error is around 70 centimeters across like 20 gauges. We did this 2024 event across Los Angeles and got around a 60 centimeter error across 20 gauges. Memorial Day flood in Miami was around 15 centimeters. That looked a little bit better, but when it's tidally driven, it tends to be a little bit easier to get that right. The best flood extent accuracy that we've been able to get in these urban conditions is around 70% critical success index. So that's what I got, and I want to thank you everyone for your attention, and hopefully there's time here to chat for a little bit.
Yeah, well, thanks a lot, Brett. There are a couple of questions. First of all, anybody who has questions can type them into the chat or raise your hand. There are a couple of questions in the chat already, which I can read. John Nielsen Gammon asks, what's the role of the fluvial data in the modeling?
So for the LA model, we used gauge records to estimate 100-year return period flows, and then assume that those 100-year return period flows were in the channels to look at what would flood. First Street and Fathom, their methods are similar. They do it at a different scale. They tend to set up reach scale models, and they try to estimate what the flood peak is in the stream, and then look at what's going to flood for that particular flood peak. Our method was at that time was to use the gauge records. We felt like the gauge records in the streams were the best predictors of fluvial flood risk, and we tried to kind of make that work with this 2D modeling system. But there's some complications there, so which is something we're working on in another paper. But does that answer it well enough?
If I could follow up. So you're essentially you're running the model, and when the model is producing a flood level that corresponds to the 100-year flood value at the gauge, that's what you then use to estimate the footprint of the 100-year flood?
That's
okay,
right.
Thank you.
Yeah. And then we do this composite. We run separate scenarios for the rainfall-driven flooding, which we call pluvial, the sort of stream flow-driven flooding, which we call the fluvial, and the coastal flooding. So we run those as separate 100-year return period scenarios, and then we take the maximum across those three scenarios as our composite, flood hazard depth for the region.
Can I have a brief follow-up to that while we're So that's the way the meteorology comes into it, more or less. And I'm just wondering, since you focused on what's downstream, the hydrology downstream of that. So if we wanted to understand the disagreements, between different estimates of the 100-year risk, do you have any sense of the relative importance of those two things? I mean, can we assume that the values of the 100-year, rain event, for example, are similar in these data sets, or are they not? And is that as big an issue as the flood modeling?
No, I think you're getting at like some of the really interesting questions, which deserve like more attention. How do we think about a 100-year flooding event with like a spatially distributed watershed scale model? One of the conventions that has been used in the risk mapping space is to use NOAA Atlas, 14 or whatever precipitation rainfall intensity data, and design concoct something called a 24-hour storm, which may or may not be consistent with like the nature of flooding in that particular area. And I think that kind of an approach has been one of somewhat of I think the engineers would say, like, we are trying to approach this, we have to do something that's efficient and reasonably conservative. And so you end up with like sort of unsatisfying ways of setting up the models when in fact rainstorms propagate over watersheds in different ways. So we're in the midst of trying to rethink that a little bit and kind of try to report in a scientific way, like how differences in the way you kind of combine your rainfall forcing with your hydraulic modeling can give you different types of answers, and how big of a difference does it make, sort of. The other thing that I think is what Eva Martin is really diving into with her work is that there's also a different scale of modeling, like historically, like FEMA mapping they do a reach at a time. And I think that the large scale cat risk models, they also do kind of river reach segments. And they tend to do a hydrologic model to predict what the flow peaks are going to be for each segment, and then run the hydraulics for that segment and move on to the next segment and try to piece them all together like a quilt. It's like a quilt of information you're knitting together. But now our model allows us to try to tackle a little bit bigger area more efficiently. So it kind of opens up some opportunities to do that a little bit differently up to the scale of the watershed, for at least watersheds the size of the Los Angeles River. We couldn't do the Mississippi watershed. That would be a bit too much for one model. Sorry, I can't give you a robust answer, but I think I can compliment you for a wonderful question.
Yeah, so Monica Morrison says, respect to the error, it seems that the First Street models overestimate flood, which it could be argued is better. A false positive is preferable to a false negative, as underestimation could lead to great harm to property. Wondering if discussions about preferences for error are discussed with users.
Yeah, that's a really, really interesting question. So I'm trying to like separate like whether something is more or less accurate and whether something's more or less preferable, to a user at this time. But certainly, the bigger flood zone you have, the more, the sort of larger the categorization of who's at risk, and certainly that can maybe be beneficial. But on the other hand, if it's a forecast or something like that, and you have false alarms, and people are ticked off that and they learn not to trust you because your predictions aren't accurate, then you run down that rabbit hole. I guess you would all know in the atmospheric community much better than me about like the issues with forecasts and being more conservative and less conservative. So I really don't know whether it's preferable to be on the wet side or the dry side of an estimate. But I guess right now I'm just trying to figure out like how do you make it as accurate as possible and then go from there.
So the next one is from Sarah Santa Maria Aguila. Sarah, do you want to say it, or?
The question is just asking, is the Primo model publicly available?
It's not publicly available, but it's available for collaborations. Problem once you share it, then everyone writes to you with their bugs, and I can't. I have no resources to stay on top of all of chasing everyone's bugs down.
Oh, so you mentioned you've done a Harvey run. You've done these runs. Are the outputs of those? Are you willing to share those with people? Or
oh, sure, yeah, sure.
See, Kelly asked a question. Have you tried to do a population corrected measurement of risk? For example, steep areas are hard to model, but often less populated. So dense areas have complex infrastructure. So a miss there might matter more.
So this is basically getting at, you said that steep slopes show up and they look bad in flood models, and that's common across more than just the first street model, for what it's worth. And then, but that missing drainage infrastructure matters a lot in certain areas. I guess what I'm wondering is, if like 8 people live in the hills, I know that's not the case in LA, but it's the case in a lot of places, but you have a densely populated urban area, I think you probably have this information since you reported demographics in that same paper, but like the percent population that's exposed to error, I guess is where I'm going. Like the relative merits of the things that you miss, because I will say drainage infrastructure is a much harder piece of information to collect than slope.
Yeah, so I haven't tried to explore that kind of ranking or prioritization. Sense has been that that is something that agencies will think about, and when I've shared my work with California Department of Water Resources, especially kind of the exposure piece and disadvantage, who's exposed from a disadvantage perspective. What they thought was really interesting is that like with this type of a model, they could they could target their help more effectively to different cities. So like they could look at a city that your municipality that sort of needs this type of assistance. We have this funding program that's designed for your type of problem, which is like maybe sort of high vulnerability, low level hazard sort of combination. And then we have these other cities where you have really high hazards, and those are the ones that we need to go with this program. So they kind of looked at it as like this type of data is really helpful for us to sort of match the community need with the right like funding program and the right resources. So I thought that was sort of a nice lesson about why sort of parsing the hazard and exposure and the disadvantage and things like that in a connected way was valuable.
For what it's worth, there's sitting on the insurance side, there's very little sort of national scale information about things like stormwater infrastructure. And so we largely have to make assumptions using things like population density, which is obviously a terrible way to do that, because that means that when cities then invest in upgrading their infrastructure, very difficult to show that they've gotten credit for it, right? It's hard to incorporate that into modeling because we'll never hear about it, right? It's buried on some cities like webpage somewhere for like this town is the right. There's not a consistent source of information for that. So being able to demonstrate that, hey, if you can actually publicly share this information, it'll show up in a whatever percent reduction, 80% reduction in your population that shows up as exposed to flood. That could be a really compelling way to improve the transparency of that data.
Yeah, I appreciate that point, because like we had that primo versus primo drain comparison. You can see the big reduction in at least, you know, fairly substantial
And
reduction
very
in
uncommon
flooding.
to have that side by side. So
Yeah,
really stuck out.
And so certainly if there was updated information about infrastructure, then you could go on to demonstrate further benefit, right?
Let's see. So the next question, Paul Ulrich asks, how many different hydrologic models are available for performing simulations similar to Primo and FSF? If resources were boundless, would you recommend a model ensemble instead of using a similar model? Is translatability between regions primarily limited by cost of calibration?
Yeah, well, I think that the sort of freely available model that is like HEC-RAS, right, that can be used in different areas and supported by the U.S. Army Corps. So it has you know, functionality that a lot of people are familiar with, and there's number of commercial models that people turn to. There's open source models like I mentioned the Sphinx model, which is growing in popularity as a fast flood modeling tool. And there are like the Triton model, which I think came out of the Mario Morales it was at one of the national labs. So put that out there. So there's a number of models out there that are solving similar equations, and none are quite like Primo in the sense that it has the dual grid method that could allow you to more efficiently scale up. And now it's sort of running on a GPU, so it's kind of a nice self-contained approach. But the question, what was the second part of that question?
Yeah, I was just curious as to whether or not you would recommend actually using model ensembles in the future.
Oh,
It
yeah.
seems like one of the issues that perhaps First Street ran into with Zillow was that it's only a single model output, right? And so we don't really know how it compares to other models that maybe have different, better capabilities in different regions.
Yeah. In terms of ensembles, I'm more interested now in ensembles from different forcing, right? If you propagate like possible forcings like atmospheric forcings or coastal forcings, you know, through any model, and I think that if you knew the uncertainty, what's the uncertainty in your drainage representation, if you knew what's the uncertainty in your precipitation forcing, I think that it'd be more interesting to start there with a model before you sort of just start putting lots of different models with different data structures in there, because I think you could more systematically like understand the sort of more sensitive factors driving uncertainty.
Alex asked a question. Do you want to ask a question, Alex?
Sure. I was just curious what it was like working with the First Street models and data, and how feasible are these types of intercomparisons. It seems like we've been batting around the idea of trying to encourage MIPS, we call them, but wondering if this is something we should be thinking about in the flooding space.
Yeah. Well, the data that we had access to was easy to work with, and we accessed it through a process that First Street had set up. They had a process where you could write a proposal and say, you're interested in doing some comparisons and doing work with the data. And so they reviewed that and approved access to their data for us in Los Angeles and allowed us to do that. And I think that was a great program on their part to let that happen. Something that once we had access to the data, it was easy to work with. It was organized in a real similar way to the way we might have like raster grids of flood depth and things like that we could work with.
Thanks a lot, Brett, and hopefully everybody learned a lot. Thank you. Bye.
Okay. Bye-bye, everybody.
Thanks, everybody.